In this section, we are going to go back to a method that we saw in Chapter 1, but add some further detail to it. And this is talking about how to compute power limits that are primarily voltage-based using a very simple cell model. The method is referred to as the hybrid pulse power characterization test, or the HPPC method. And this was specified by the Partnership for New Generation Vehicles, PNGV, which I believe eventually became Future Car and so forth. So this was a consortium of government entities and the three major automakers in the US that put together some standards for how to compute different things, and this is one of them. The idea is to come up with an equivalent cell resistance over a time horizon delta t, and then use that resistance with a V equals OCV minus IR, very simple cell model, to predict the kind of power that I could withdraw from the cell or put into this cell over delta t seconds and not cause an excess voltage. The tests that we do are illustrated in this figure on the right, where we have the cell resting before the test begins, and then we subject the cell to a pulse of discharge current for delta t seconds, where delta t is the time horizon that I'm required to predict over. And the difference between the voltage of the cell, delta t seconds after the beginning of the pulse, and the voltage before the pulse began, that delta V is called delta V discharge. And we compute this equivalent series resistance that, as you notice, has the R0 term in it, but it also has diffusion resistance terms built into it too, because the voltage does change over those delta t seconds, primarily because of the diffusion voltages changing, but also somewhat due to the OCV changing. We allow the cell to rest probably longer than I showed, so we start at equilibrium again, and then we subject the cell to a charge pulse, and we measure the voltage before the charge pulse and then delta t seconds later, and then we compute a charge resistance, which is this delta V charge divided by the charging current. And we can tabulate resistances versus different states of charge and different temperatures and come up with a nice fancy table of resistances that I could use in a power calculation. We will assume, or they assume, in this methodology, a very simple cell model. This is the cell model that is used. We have an open circuit voltage, and we have a resistance. And so you can see that the diffusion terms and hysteresis terms are completely ignored in this model, although arguably diffusion is taken into account somewhat, because this resistance is either this R dis delta t or the R charge delta t, depending on whether I'm computing discharge or charge power. So over the time horizon delta t, we are considering, at least crudely, some of the other terms of the model, but we write the model as a simple voltage source and resistance. In the equation, then, we've got voltage is OCV minus I times R, and I can solve for I is OCV minus the actual voltage divided by R. When we're computing the power estimate, we assume at the beginning that our concern is to keep terminal voltage between Vmin and Vmax. So to compute the discharge power, we set resistance equals R dis delta t. We say V equals Vmin, because that it would be if I was somehow able to clamp the voltage at Vmin, I would be getting current out of this cell that was the maximum current I could get without exceeding Vmin, without violating Vmin. So the current is OCV minus Vmin over R dis delta T. And then the discharge power at this step in the computation is maximum discharge power, is the number of cells in series times the number of cells in parallel, times this Vmin. Remember, power of a cell equals IV. V, we are clamping at Vmin, so that's the V part, and then I is this computation here, but I need to be careful because not all cells are the same, so I have to take the minimum I to make sure that none of the terminal voltages exceed the Vmin. So when I do this, this Vmin power is not actually, or Vmin voltage is not actually achieved by all cells. It's achieved only by the cell that minimizes this. So in a sense, I'm underestimating the actual power that could be available, but I am making sure that I'm a little bit conservative by taking the minimum of those currents. To compute charge power, we do the same kind of thing. I set the resistance equal to R charge, and I clamp, that should be max, I clamp the voltage at V of t equals V max. When I compute power this way, we get, notice that OCV itself is going to be less than Vmax, and this voltage Vmax is going to be bigger, so the numerator here is going to be less than 0, the resistance is going to be greater than 0, so the overall charging current is negative. So a bigger charging current is even more negative, and that can be kind of confusing, but the maximum magnitude current is the minimum signed current when I'm talking about charging current. And then the pack charge power is going to be Ns times Np as before, times Vmax, and then times the maximum of all of these, which is a minimum in an unsigned sense. So same idea, just with a slightly different computation. We saw that, or essentially that, in Chapter 1. Now we're going to add some refinements to allow us to put limits not only on voltage, as we have done here, but also on state of charge, on maximum current, and maximum power design limits as opposed to dynamic limits. And that's quite simple to do. So we keep this computation, we don't throw it away, but we consider also how is state of charge going to change over the next delta t seconds based on a constant current. So Z sub n, the state of charge of cell n, delta t seconds in the future is the state of charge right now, minus the Coulombic efficiency times delta t over Q, all times the current going through this cell. And we can assume that the Coulombic efficiency is 1 for discharge and some value eta, which is less than or equal to 1 for charge currents. So if we have some a priori design limits on SOC that state you should never get SOC lower than Zmin or bigger than Zmax, we can also compute current to enforce these limits. So take this equation and solve for current. I have Zn t plus delta t minus Zn of t over eta delta t over Q equals minus In. And that allows us to think, well, if I want my future SOC to be between Zmin and Zmax, I can clamp it at that value, at Zmin or Zmax, and see what value of current is going to achieve that. And that's what we've done here. We've said, okay, this is the present state of charge, and the future state of charge I will clamp at Zmin to give me the maximum current allowed for this cell, looking at SOC only, not looking at voltage or anything else, but looking at SOC only, the maximum current for this cell such that in delta t seconds I don't violate Z min. And the same thing we do for charge, except we put Z max instead of Z min, and we put the coulombic efficiency in, and we get the current for that. We don't know Z of t perfectly, the state of charge of the cell. So we can use any kind of side information from our SOC estimation algorithm, such as the error bounds on that SOC, to help make power limits more conservative or more robust or safer, to subtract or out, or to kind of say when I'm charging, here's SOC versus time and then some bounds on it. When I'm computing charge power, I use SOC plus 3 sigma in my computation. And using discharge power, I use SOC minus 3 sigma, so that I can say I'm quite confident that I'm within those limits, but I don't know if I'm at the upper limit or the lower limit. I'll assume the worst case for both computations. So discharge power, computed to enforce an SOC limit, takes the state of charge estimate from maybe a Kalman filter, subtracts 3 sigma, and uses that as the SOC estimate. It uses this value for discharge. And for charge, takes the SOC and adds 3 sigma, uses this value here when computing charge power. Once we have computed cell current limits for voltage and for SOC, the pack currents for discharge and charge can be computed like this. So the maximum discharge current is the minimum of all the other maximums. Well, it's the minimum of all of the computations we've made, because if any of these computations is achieved exactly, that's going to exactly hit some voltage or SOC or current limit. So I want to make sure that none of them are hit, or just one at most. So I have to minimize them. So the maximum discharge current is the minimum of the design current limit for maybe wire sizing or something, or the SOC-based limit, or the voltage-based limit. When I'm computing charge current, remember that it's negative, so the minimum in magnitude is the maximum in assigned sense, so I have to use maximum here instead of the design current value, the SOC computation, and the voltage-based computation. Now these mins and maxes are very tricky. You have to put in a few numbers to work it out, and it's so tricky I did it wrong here, so I have to fix it. That I believe should be max, and that I believe should be max, and that I believe should be min, and that I believe should be min. But let's see what we're doing now. We've computed the current limits. Now we have to compute the power limits. Looking at charge power, which is a negative number, we want to take the number of cells in parallel and multiply by the maximum of whatever is left. Remember, that's going to be the minimum in an unsigned sense. And what's left is the number of cells in series times the maximum absolute, or the p-min of a particular cell, and the summation of the powers from all of the cells. So it's the minimum in magnitude, or the maximum in assigned sense, of what is the actual power limit, the a priori fixed power limit, or the power that uses this number here as the current that is the most I can use. So that current times a prediction of the voltage delta t seconds in the future is the power of that particular cell, the nth cell, but I sum up for all nth cells to get that total of voltage times current to compute that total power of the pack. To compute the Vn, the terminal voltage of cell n delta t seconds in the future, we use our simple cell model, and we say that it's equal to approximately, not exactly, but approximately equal to the open circuit voltage delta t seconds in the future, which uses the state of charge update equation to determine what that is, and it uses the current times resistance of the cell in the charge sense. The maximum discharge power is very similar. I take the number of cells in parallel and multiply by the minimum of these other powers, which is either the number of cells in series times the maximum rated power of a cell, or the summation over all the cells in series of the maximum current I've computed as possible times the future voltage of that cell, and the future voltage of that cell is the future OCV of that cell, and the minus the current times the resistance of that cell. So this overall is the HPPC method, or the most general version of it, where we do these pulses to characterize the resistances of the cell. And once we have these resistances and limits on voltage, current, power, we plug them into these different equations to find the limiting current voltage-based, the limiting current SOC-based, and the limiting current that is just the design limit. Combine all those together to get an overall limiting current, and then plug it into these charge and discharge power calculations to get the overall power limits for the battery pack. That is pretty much state of the art. I will say that there are a lot of approximations made with this method of assuming that the cell model is very, very simplified and so forth. So the number that comes out of this calculation is very often multiplied by some factor, a derating factor in real life. So I would take the power reported, the value that I give to the vehicle is, say, power max discharge times derating factor, where this might be a number, say, 0.9, so that I allow myself 10% inaccuracy in my computation based on all the assumptions that have been made to get to this point. In the next section, we will start looking at a different method that uses a more accurate cell model, so can more accurately predict the power available in a cell. So let's get going and look at that.